My dear friends, welcome to Rajashekar classes on Applied Data Science with Python. This is lecture number 227. In this lecture, we will try to understand geometrical interpretation of column standardization. I already discussed concept behind column standardization in my previous lecture, that is lecture number 226. I request you to go through this lecture before understanding geometrical interpretation of column standardization. I also request you to go through lecture number 219, in which I discussed about column normalization. In this lecture, I discussed concept behind column normalization, and also I discussed geometrical interpretation of this geometrical interpretation of this column normalization. If you understand column normalization, understanding column standardization is very simple. Both of these methods, both of these techniques, which methods? Column standardization and column normalization, basically they are pre-processing techniques. Otherwise, I can say pre-processing methods. In this lecture, I will discuss about geometrical interpretation of column standardization. If I have two features, heights and weights of students in some scale, I don't care about the scale. That scale may be in meters. That scale, let me say first, this is F1, feature 1. Heights, these heights may be in meters, centimeters, that may be in some scale, I don't care, in feet. There is another feature F2, weight. W means weight. This may be in kgs, this may be in lbs, this may be in grams. I don't care the scale of this particular feature. Now, let me plot this data, isn't it? After plotting this data, I will try to calculate mean vector. Let me say this one is my mean vector. Then what is standard deviation? What is variance? So if I project each of these points onto, let me say I am projecting all these points onto height axis, onto x axis, onto feature 1 axis. I can keep on projecting all these points like this, isn't it? Let me project like this. Yes, I am projecting. Therefore, where can I get? This is mean. Therefore, this point, I am assuming this is mean, isn't it? This point, what is this point? What it indicates? If I keep on, if for each point, I can project it onto x-axis. If I keep on projecting points on x-axis, the mean, this is mean, I can say this one is mean height. Can I say this is mean height? Yes, this is mean height. What about mean weight? In similar manner, I can keep on projecting all these points on feature 2 axis, that is weight axis. If I keep on projecting, what happens? Just see, this is the point, this is a point, isn't it? If I keep on projecting like this, this particular point is known as, what it indicates, that feature 2 is, it's a weight. Therefore, I can say this point indicates mean weight, isn't it? Now we have got mean height and mean weight. Then what about the variance? This one, let me say like this. What about variance? This is variance. This part is known as variance. Yes, this portion is known as variance. Variance on which axis? On x-axis. or I can say variance on height axis. In this length is this portion, this part is known as variance on height axis, or otherwise I can say on x-axis. In similar manner, what is the variance? This is the variance. Variance on which axis? Variance on weight axis, isn't it? Now, by transforming, this is my original data. By transforming this using column standardization, what do we get? We will try to understand column standardization. Let me rewrite. This is my original data. Let me say like this. Let me say this is feature 1. As I told you, this is my feature 1. What is my feature 1? Heights. What is my feature 2? My feature 2 is weights. Isn't it? Where is my mean weight? As I told you, I must keep on projecting here points. If I keep on projecting, I will get some mean height and mean weight. Isn't it? Yes, I am repeating. Just bear for few seconds. This point is known as mean height. Isn't it? This is mean height. In similar manner, I can project like this. I can project like this. I can project like this. All these points. In similar manner, if I keep on projecting points like this, in similar manner, somewhere here, what will I get? I will get mean weight. As I told you, what is my variance? This portion is my variance of original data without column standardization. In similar manner, here I will get this portion is variance of weights. Isn't it? Now, let me apply column standardization on this particular data. How can I apply column standardization? Let me apply column standardization. If I apply column standardization, just what happens? Now, this features F1 will be converted. Let me say this F1 is F1 dash, that is, let me say H dash. What is my F2? F2 becomes F2 dash. Let me say that is W dash. Now, what is column standardization? I told you that in my lecture number 226, that is in my previous lecture, we were saying that we were discussing about column standardization. What is the meaning of column standardization? I am going to get mean of 0. That is, mean is 0. Please refer my previous lecture. Mean is 0, and mean is 0 for new data, and also your standard deviation or variance must be 1. That's the basic meaning of column standardization. For my new data, my mean of my new data must be lie at 0. I can say, let me say like this geometrically, if this is original data, mean this will move to here. Therefore, this is 0, 0. This mean will become 0. Mean of transformed data or mean of new data must be equal to 0. I transformed my space. I have basically taken these points, original points. I have basically taken these points such that mean moves to 0. These points mean moves to 0, isn't it? And standard mean is 0 and standard deviation is 1. I also squished these points. I also compressed these points, so that first thing what I did, I moved my mean to center. First point is I moved my mean to 0, 0, and I'm squishing these points. Otherwise, I'm compressing these points so that standard deviation, such that the variance or standard deviation is 1. I get now this spread. Just see the standard deviation. I can say what is standard deviation here? This is standard deviation, isn't it? This is spread. This is known as spread or standard deviation or variance, isn't it? In my new space, this value is 1, isn't it? On weight axis, in similar manner, what about on x-axis? This spread, or I can say this spread or variance, this is spread or variance or information, all of them got same meaning. This must be 1 on weight axis as well as on weight axis, on y-axis as well as on height axis. Now literally what I am doing, moving the mean to 0. That's first point. I am compressing, I am squishing these points. I am squishing or compressing this point so that standard deviation is equal to 1. The standard deviation, this need not be squished, this need not be compressed. Sometimes what happens, if original data standard deviation is 0.5. Therefore, in that case, what I have to do? I have to convert sigma dash, that is standard deviation of transformed data. New data must be 1. In that case, what I have to do? I must expand it. For example, in the case of original data, sigma equal to 5 means your variance, your spread, your standard deviation is equal to 1. In that case, your sigma dash must become 1. Therefore, in that case, here, in this case, I must compress. So that resultant data standard deviation is 1. In this case, sigma equal 0.5. In this case, I must compress data, original data, so that standard deviation of new feature, new data must be 1, isn't it? These 2 points are important. Which points? Moving mean to 0 and I am adjusting standard deviation is equal to 1. These 2 points are essence of your column standardization geometrically. Just if you repeat this one, I think I need not repeat. These 2 points are important. I can say like this. So I will squish if the standard deviation. I will compress. When can I compress original data? If the original standard deviation is greater than 1. If sigma is greater than 1, then what happens? In that case, I will compress. In that case, what will I do? I will compress so that sigma dash equal to 1. If sigma is less than 1, I will expand so that less than 1 means so that your sigma dash transformed data standard deviation is 1, depending on this one. Our idea is transformed data must have standard deviation. As I told you in my previous lecture, if it is standard deviation is 0, mean is 0 and standard deviation is 1 means that can follow standard normal distribution, which has got many more benefits if you transformed into standard normal distribution. We already discussed what is standard normal distribution. I can say this is often called mean centric. Why? Because you are centering the mean at origin. Your transformed data mean is at origin. Centering the mean at origin followed by scaling. How am I scaling? You are scaling it such that mean centric basically is nothing but moving the mean vector to origin. Scaling basically means you are ensuring that standard deviation on every axis is equal to 1. Standard deviation for all features equal to 1. We will see why this is useful, why standard deviation is very, very useful when we learn about PCA, which I already discussed basic concepts on PCA. Again, I will make use this concept in next lectures on principal component analysis. Thank you very much.